So just like indices, logarithms also have their own set of rules. And there's several, and we're going to prove each one and then apply it in a question. So we're going to start off with the additive rule. Now the additive rule of logarithms says that, so if we let x be equal to log to the base a of m, and we let y be equal to log to the base a of n. Okay. Then if I convert both of these into indice form, then on the left, I'm saying that a to the power of x is equal to m. And on the right, I'm saying that a to the power of y is equal to n. And well, what happens if I multiply m and n together? Well, m times n is just a to the power of x times a to the power of y. In other words, m to the power of n is a to the power of x plus y. So that's just our indice law there. Well, I can rewrite this back to logarithmic form. So I would be saying that log to the base a of mn is equal to x plus y. So in the introductory video to logs, we saw that that's how we can convert back to the logarithmic form. And well, x is just log to the base a of m. We've got that, we denoted that up here. And y is just log to the base a of n. So if I just copy this down underneath, we're saying that log to the base a of m times n is the same as log to the base a of m plus log to the base a of n. And in fact, this is going to be really important, and this is going to be one of our log laws. And we're going to see that in practice now. So if we take on a question which uses this, let's say that we need to look at, well, what is log of 50 plus log of 2 equal to? Okay, well remember that if I don't have a base in my log, then we're looking at log to the base 10. That's just one of our notation rules. So this question is just the same as log to the base 10 of 50 plus log to the base 10 of 2. Okay, well the rule here is I have the same base, and in my rule I have the same base, so in this case a is equal to 10, and my m would be 50, and my n would be my 2 here. And the rule says that I can just write that as log to the base 10 of m times n, so 50 times 2, which is just the same as log to the base 10 of 100. And well, if we ask ourselves, what do we need to put 10 to the power of to get 100, then the answer is 2. So log to the base 50 plus log to the base 10 is equal to 2. And that's using this additive law which we've just come up with. So that's going to be really important. We've looked at a little proof to where we get it from, but from this point forwards, it's going to be about our ability to apply that in questions. Let's look at another one. The next one is the subtractive law of logarithms. So let's let, again, x be equal to log to the base a of m, and we will let y be equal to log to the base a of n. Well, once again, if I convert these into indice form, we're saying that a to the power of x is equal to m, and we're saying that a to the power of y is equal to n. Now, instead of multiplying m and n together, let's divide m by n. So m over n, well, that's just equal to a to the power of x divided by a to the power of y. And another way to just write that would be a to the power of x minus y. So we've got this expression that m over n is equal to a to the power of x minus y. Now, if we write that as a logarithm, so back to the logarithmic form, we would say log to the base a of m on n is equal to x minus y. But we know that what x is and we know what y is, so we can say that log to the base a of m over n is equal to log to the base a of m subtract log to the base a of n. And that is our sort of difference rule, or our subtractive rule of logarithms. Okay, and if we wanted to apply this rule, well, let's take on the following problem. Let's look at what log to the base 4 of 160 minus log to the base 4 of 10 is equal to. Well, by the rule, we see that we've got the same bases. So here, the same bases. And our m in this case would be 160, and our n in this case would be 10. And my rule says that I can just write that as log to whatever my base is, so keeping my base the same, which is 4, of m, which is 160, divided by n, which is 10. So I'm now trying to find what log to the base 4 of 16 is. So we ask ourselves, what do we need to put 4 to the power of to get 16? And the answer is 2. So log to the base 4 of 160, subtract a log to the base 4 of 10 is just 2. So we've looked at the additive rule, the subtractive rule, or the difference rule. Finally, we've got one more rule. So this one is called our power rule, which is a little bit different. So let's let log to the base a of m to the power of k be equal to x. Then, if I was to convert this back into the indice form, I would see that a to the power of x is equal to m to the power of k. And now to isolate my term m here, I can raise both sides to the power of 1 over k. So I just isolate my m on the right hand side, and my left hand side, when I multiply x and 1 on k, I just get x over k. So we now see that a to the power of x on k is equal to m. And now if I put this back into a logarithmic equation, I see that log to the base a of m is just x on k. So if I multiply both sides by k, I see that k times log to the base a of m is equal to x. And I know what x is equal to. So k times log to the base a of m, we denoted that at the start to be log to the base a of m to the power of k. So this is what we call our power rule of logs. And if we look at a little example, so let's say that we're asked to work out what log to the base 3 of 27 squared is. Well, before we knew this rule, we would be looking to try and work out what log to the base 3 of, and then you would have to do 27 times 27, which without a calculator is no fun. We most definitely don't want to be doing that. However, with this rule, if we compare what this bit here looks like in comparison to the right-hand side of this equation, we can see that they're identical. Our a is our 3, our m is our 27, and our k is our 2. So I can write that as it appears on the left-hand side. So I can rewrite log to the base 3 of 27 squared. I just bring my power out the front, and I end up with 2 times log to the base 3 of 27. And well, we know that log to the base 3 of 27, what do I need to put 3 to the power of to get 27? And the answer there is 3. So we just get 2 times 3, which is 6. So log to the base 3 of 27 squared is just equal to 6. So they're the three main rules that we've got. We've got the additive rule, the subtractive rule or the difference rule, and we've got this power rule. There's a couple more little points that I just want to make before we dive into some questions. So one of them is that log to the base a of a is equal to 1. And that kind of makes sense. What do we need to put a to the power of to get a? And well, the answer there is 1. Anything to the power of 1 is just itself. And if we see this with some numbers, then if we try to work out what log of 10 is equal to, well, we know that log is just log to the base 10 of 10. What do we need to put 10 to the power of to get 10? The answer is 1. Likewise, if we look at the natural log of e, ln, or the natural log, is log to the base e of e. What do we need to put e to the power of to get e? Again, the answer is just 1. Let's have a look at the next one that says log to the base a of 1 is equal to 0. And I think we saw this in the introductory video. We're basically saying here that anything to the power of 0 is equal to 1, right? If we converted this to an indice rule, we're saying that a to the power of 0 is 1, which we know is true. And likewise, if we converted this one here to an indice rule, we would be saying that a to the power of 1 is a, which we also know is true. So that's just a couple of indice rules which we know being converted into a logarithmic equation. Another one is that we could say that the log to the base a of 1 on b, well, I can rewrite that as log to the base a of b to the minus 1. And our power rule saw that I can actually pull this negative 1 out to the front here. So log to the base a of 1 on b can actually be just written as negative log to the base a of b. So that's another rule to be aware of. For example, log to the base 7 of, let's say, 1 on 49. Well, that's just equal to negative log to the base 7 of 49, which is just negative 2. Okay, one more that we might have where we can actually change the base to something that we desire. So log to the base a of b, we can actually write this as log to the base c of b divided by log to the base c of a, where we then get to choose what that base might be. Where would we see this in action? Well, let's try and take on the following problem. Log to the base 9 of 27. Well, one way to do that, which we already know, would be to write this as an indice equation. So solving for when that is equal to x, solving for x. Well, writing that as an indice equation, we're looking at when 9 to the power of x is 27. Okay, and if we rewrite 9 as 3 squared, and we rewrite 27 as 3 cubed, then we're solving for when 2x is equal to 3, and we see that x is 1.5. Alternatively, we could rewrite this using this part of the equation as log to the base 3 of 27 divided by log to the base 3 of 9. And the reason I chose a 3 as my value for c here is because it works quite nicely with both 9 and 27. You wouldn't choose a base or a c value here of 4 or 5 or something silly like that because you wouldn't be able to do much with it. Now we know that log to the base 3 of 27, what do we need to put 3 to the power of to get 27? The answer is 3. And log to the base 3 of 9 is just 2. So that answer is 1.5. So more than one way to solve these problems. Could have converted into an indice equation, or you could have used this rule here if that popped out the page at you. So that's it for the rules. What we'll do is we'll put all of the rules together, and then we'll try one final question which gets us to apply them. So here are the three main rules that we have for our logarithms. We have the additive rule, which we looked at, the subtractive rule or the difference rule, and the power rule. Let's now say, so we're going to let x be equal to log of 3, and we're going to let y be equal to the log of 2. Okay, can we find, in terms of x and y, what log of 6 would be? Well, if we look at our 3 and our 2, we know that 3 times 2 is 6. So we're kind of looking at this rule here. So we can say that log of 6 is equal to log of 3 times 2, which is equal to log of 3 plus log of 2 by our first rule. And log of 3 is just x, and log of 2 is just y. So our answer to log of 6 in terms of x and y would just be x plus y. Similarly, if we were asked to find what log of 0.66 recurring was, we know that that is equal to log of 2/3, which is log of 2 subtract log of 3. And well, log of 2, that is equal to y, subtract log of 3, which is x. So there we're just using our difference rule. Let's have a look at another one. Let's look at what a log of 81 would be. Well, I can rewrite 81 as 3 to the power of 4. And using my power rule that I have here, I can write that as 4 times log of 3. And log of 3 is just equal to x, so log of 81 would just be 4x. And finally, if I just zoom out a little bit, we'll have one more example. Log of 2 root 3. Well, I can write that using the additive rule as log of 2 plus log of root 3, which is good for this component because I've got my y. Okay, but this component here doesn't look as good. But I can rewrite log of the square root of 3 as just log of 3 to the power of a half, which, using my power rule now, so we're combining two rules in one question here, I can write that as just a half of log of 3. And log of 3 being x, so my final answer would be y plus a half of x, or y plus x on 2.